All right, just a walkthrough of the Ocean Acidification Study Guide. So I'm going to fly through some of these. Right here from 1 through 13, I want you to use formulas. It really starts off with carbon dioxide combining with water to form carbonic acid. So that's CO2 plus H2O, creating H2CO3. Now, H2CO3 is unstable, going to dissociate, basically split apart. Look at your beads. Good place to go look. And it splits into the hydrogen ion and the bicarbonate. Now, if I'm branching off over here, pH is a measure of how many loose hydrogens there are from the dissociated carbonic acid. Now, the more hydrogens I have, it causes a drop in pH, or the pH to get closer to 0. The less hydrogens I have, it causes an increase in pH. Over here is just making sure you know an increase, so more hydrogen ions is going to make the water more acidic, and a pH between 0 and 6.9 is acidic. So 5 and 6 are basically the same answer. Over here on number 7, with less hydrogen ions, this makes the water more basic. A pH between 7.1 and 14 is basic, so 8 and 9 are the same. Coming over here, it starts talking about bicarbonate. So bicarbonate is unusable by calcifiers. What are calcifiers? Those are animals that have a shell that combine calcium and carbonate, which are both floating in the water, separate from one another. Those calcifiers take them, they combine them to form calcium carbonate. Now, one of the things here is bicarbonate, or H2CO3, is unusable by calcifiers. How come? Because the H2CO3 cannot bind with the calcium anymore. All right, over here at number 13, loose hydrogens will steal carbonate from the water. Now, this is really important. Now, 13 and 11 are connected. Calcium is separate from carbonate floating in the water. Like I said, they will take the two of them and combine them to create a shell. Unless, now if you go to your big grid inside of your notebook, it shows how the loose hydrogen will steal the CO3 from the water. Okay, it'll take it away and the calcium can't combine with it anymore. All right, moving on over here to number 14. So in the lab, we increased acidity, okay, by adding more CO2. So that's how we increased the acidity. Now there is an indirect relationship between carbon dioxide and pH. Again, as carbon dioxide goes up, pH begins to drop. Now pH would drop slower in ocean water compared to pure water because of the carbonate that's floating around in there, the CO3. So that comes over here. Again, it's really important that, like I said, you can connect these. So that CO3 that's floating around can actually slow down the drop in pH. Now, coming over here to number 15, oh, here it is. It's kind of over here somewhere. So we know that the primary cause of ocean acidification is carbon dioxide, or CO2. Now, ocean acidification has actually helped slow climate change or global warming, whatever you want to call it, by absorbing that excess CO2. So we know about 25 to 30% of carbon dioxide is absorbed into the ocean. So on the test tomorrow, if you say 25%, you're fine. If you say 33%, you're fine. So again, if you're within that range, you're okay. Now, before the 1800s, the pH was under 8.2. Even if you said 8.2, you're fine. But we estimate that by 2100, that pH might change to 7.5. Again, this is a range. If you put anything between 7.2 to 7.8, totally fine. Over here, so that was number 29, big jump. But over here at number 18, lower pH makes it harder for shellfish to form, or you could put it's harder for shells to form. In some cases, shells will dissolve if the pH is low enough. All right, so let me go ahead and tackle 29 and 30. It's estimated by 2100 the pH are going to be anywhere between 7.2 and 7.8. Number 30. At this pH, it will be a base. Okay. This is a little bit misleading because they call it ocean acidification, but the ocean's never going to become an acid. It just isn't. It's going to become more acidic because it's moving away from 14, getting closer to 0, but it's never going to become an acid. All right, let's hop on over here to number 25. So for number 25, I want you to use names. So this is carbon dioxide, okay, plus water is going to give us carbonic acid. So that's the name. This dissociates into hydrogen ions and bicarbonate. Bicarbonate, again, is unusable by calcifiers because it will not bind with the calcium. So again, on the other side, on this side, I want you to use the formulas. On this side, I wanted you to use the names. Calcifiers combine, again, the word calcium and carbonate in order to form calcium carbonate. Again, for this 25 to 28, make sure you're putting the name, not the formula. And if you're having trouble with the names or the formula, just look at that gigantic grid that we put inside your notebook. It has everything for you. All right, moving on over to 31 through 39. The main factor that slows the pH fall in ocean water, again, it's kind of repetitive from up here, it's CO3. Okay, so it's CO3, that's the formula, and the name is carbonate. Now, the ocean has helped slow global warming by absorbing CO2. It's kind of what this was saying over here. If CO2 goes up, the pH will go down. If CaCO3 has increased, what does that mean for carbonic acid? So this is that critical thinking question number one, the grid. If I say, okay, this is going up, CO3, you got to go backwards up the chart, up that grid, and figure out what happened to, in this case, carbonic acid. So if the shells are increasing, that means that there's less loose hydrogens. If there's less loose hydrogens, that means that there was less carbonic acid. All right, number 35. In the shell lab, the pH was acidic on day 2 because of the loose hydrogen ions. Okay, it's still acidic. Okay, it's still acidic even on day 2. You could put that it's more basic too, but it was still an acid. Number 36. CO2 and pH have an indirect relationship. Again, that was covered earlier. 37, as plankton use CO2, just even forget the day part. As plankton use CO2, the ocean becomes less acidic because they're pulling CO2 out of the water, which kind of like this, less CO2 in the water means less carbonic acid, which means less loose hydrogens. Number 38, what is one way ocean acidification can affect organisms without a shell? This comes from your article. So this one I'm not going to tell you. So again, this one I want you to look at article number 4. So again, look at article number 4. And then how do we measure CO2 concentrations from, let's just say, 1750s or before the 1800s? We measure it using ice core data. So a couple of the resources are going to be down below. So like the tiny.cc/Avila lessons. If you're more of a video person, go watch a couple of those. Take one last look at Quizlet. Make sure you're able to go through the study guide. Get your formulas and names down, okay, so they don't confuse you tomorrow.